Hello everyone and welcome to the AI Research Roundup. I'm your host Alex, and today we're diving into some fascinating work in the world of AI and robotics. We'll be looking at a paper titled ConRFT Reinforced Fine-Tuning Method for VLA Models via Consistency Policy. So this paper tackles a really important challenge: how to effectively fine-tune these vision language action models. You know, the ones that help robots understand and act in the real world. The authors point out that just using supervised learning often isn't enough, especially when the demonstration data is limited or inconsistent. So they propose a new method called ConRFT, which uses reinforced fine-tuning. It combines offline learning from demonstrations with online fine-tuning, where the robot learns directly in the environment. Pretty effectively, it seems, achieving really high success rates. Right. And speaking of practical implementation, the authors have actually made their code publicly available, which is always great to see. This image here shows their GitHub repository for ConRFT. You can see the standard stuff, the code structure, the installation instructions, how to set everything up with Conda and JAX, and even details on the different components like the agent training and the robot infrastructure. It's really helpful for anyone wanting to try out or build upon this work. Okay, so this diagram here, Figure 1, it lays out the whole ConRFT architecture really clearly. You can see it starts with a pre-trained vision language action model, and then splits into the two stages we talked about. Stage 1 is the offline fine-tuning, CalConRFT, which uses a buffer of demonstrations to get the policy started. Then Stage 2 is the online fine-tuning, HillConRFT, where the robot actually interacts with the environment. Notice how it uses both the original demos and new data, including human interventions, in its replay buffer. And crucially, both stages use that unified consistency-based training objective. Okay, so building on that architecture we just saw, Figure 2 here gives us a look at the actual real-world tasks they use to test ConRFT. You can see there's quite a variety. Simple stuff like picking a banana or a spoon, operating a drawer and a toaster, and even more complex things like inserting a chair wheel or hanging a Chinese knot. These are the kinds of practical, sometimes tricky, manipulations where that online fine-tuning stage with human help really gets put to the test on a real robot. And this table I, really puts numbers to that testing. It compares ConRFT, both the offline CalConRFT and the online HillConRFT, against other methods like standard supervised fine-tuning SFT, and other online techniques, HG, Dagger, and PARL. We're looking at success rates and how long each attempt or episode took across those tasks we just saw. The key takeaway is HillConRFT's performance. Look at that average success rate, 96.3%, which is a massive jump, 144% better than just SFT. It also beats the other online methods pretty handily, and it's faster too, completing tasks in almost half the steps compared to the offline approaches. So, these results strongly suggest that ConRFT's two-stage approach really works well for these kinds of challenging robot tasks. So those table results were pretty convincing, right? And Figure 3 here gives us a more dynamic view of how that online fine-tuning actually progresses. These plots show the learning curves over training time, measured in minutes for 5 of those tasks. We're looking at success rate, how often human intervention was needed, and how many steps each episode took. You can see ConRFT, that's the purple line marked hours, generally climbing faster in success rate, needing fewer interventions, and solving tasks quicker compared to the other online methods shown. It really visualizes that efficient adaptation we saw in the overall numbers. Now, speaking of efficient learning, this next table, Table 2, really drives home the benefit of ConRFT's approach of fine-tuning a pre-trained model. It compares HillConRFT, which fine-tunes the VLA, against HillSearl, which tries to learn the tasks from scratch using reinforcement learning and human help. Look at the average success rates after similar training times. ChillConRFT hits 96.3%, while HillSearl only manages 31.9%. And ConRFT is faster too, averaging 30.7 steps per task, compared to 45.7. Well, this strongly suggests that starting with that pre-trained VLA and using ConRFT is way more effective than trying to learn these complex tasks from zero. Okay, so we just saw how fine-tuning a pre-trained model is better than learning from scratch. And Figure 4 digs a bit deeper into that fine-tuning process, specifically looking at how we start the online IFT stage. It compares starting the online training using two different initial models. One trained just with standard supervised fine-tuning SFT. That's the orange line. And the other using ConRFT's own offline stage CalConRFT, the purple line. We see plots for success rate and intervention rate on those pick banana and pick spoon tasks. And, well, the CalConRFT start leads to faster learning and needs less human help pretty consistently. This really shows the benefit of that offline CalConRFT stage in getting the model ready for effective online learning. Okay, so building on that idea of effective learning, Table 3 here explores whether just having more demonstration data is better. It compares ConRFT, which starts with only 20 human demos, against methods like diffusion policy and SFT that use 150 human demos, and RLDG, which uses 150 demos collected by an RL policy. And look at the average success rates across these three tasks. ConRFT hits 93.3%, which is actually higher than DPSFT and even RLDG. Well, this really suggests that ConRFT's online fine-tuning, its ability to learn from interaction, is more crucial than just having a massive initial dataset. So wrapping up our look at ConRFT, it really highlights how effectively fine-tuning pre-trained vision language models can be, especially using this consistency-based reinforcement approach. It seems much more promising than training from scratch or just relying on huge demonstration datasets alone. Well, this kind of work is crucial for making large AI models practical for real-world robotics, making them adaptable and efficient. That's all for this episode of the AI Research Roundup. Thanks for tuning in. I'm your host, Alex.